Not
All
too
right.
bad.
So, hey. So in the last video, so I just started recording, by the way. So in the last video, I started to do this well-definedness here, or to show that the left-derived functor was the same thing as the right-derived functor for Tor, and I started to develop some things for that. So just some terminology, and then I showed, and then I introduced this shifting operation. But I forgot to give kind of this one of the big applications of this homotopy, or this the chain lifting here, or sorry, the lifting morphisms to the resolutions. Okay, so and so I'm going to give that now. So in particular, I'm going to show that left-derived functors are functorial. Okay, so let me maybe do this over on the side, and then we'll go back. We'll come back to this issue here in a moment. Okay, but for now, let me do the application. Let's see. Of lifting morphisms to resolutions. So we had a projective resolution, and then so just kind of recall what happened is that so recall that given two resolutions, projective resolutions, and a map here, f from A to B, we get we get a new map here. We get some lifted maps. So here, a map from the complexes. So okay, so we get a map F bullet from P bullet to Q bullet, fitting into the diagram like this. Okay, and this map here, and the map F bullet, was unique up to homotopy. Okay, and so then there's a series of things that I want to say. Okay, so first of all, so this is chain homotopy, right? So there's a notion of homotopy between chain maps, and so let me give a kind of a bunch of little lemmas now. Okay, so first, chain homotopies. So if F is an additive functor, of okay, so I'm doing this for modules, I guess, but really this is really a thing about abelian categories. Um, and so we have an abelian category here, and let's say it just goes into some other abelian category. It's usually just R modules again, but it really is about any functor here. These are the types of functors that you can do derived functors for. Is a then and is an additive functor, then chain homotopies of complexes. So this is an abelian category, by the way. And this really, the mod R is not so important. That can be an abelian category as well. so chain homotopies of complexes are preserved under F. Okay, so so the idea here is that if so let me kind of just draw the picture here, or the diagrammatic way of saying that is that if I have some two maps of chain complexes here, and they're homotopic via some homotopy H, right? Then well, what do we get? Okay, so this whole thing under F goes to, well, we get a new chain complex by applying our functor. We get a new chain complex here by applying our functor. And we'll get two chain maps here. Okay, so all the diagrams commute, and then we'll get a chain homotopy as well. Okay, and so what's the proof of this? This is really easy, right? So essentially what you're having, so for two things to be homotopic, so a chain homotopy, right? So what is that? So that's saying that F minus G is DH plus HD. Okay, and again, the H's are the maps that go backwards, right? So we have, we have something like this: PI minus 1, QI minus 1, and then, okay, PI plus 1, QI plus 1, just to write these diagrams down again. So we have maps this way, and then the H's are the maps here, right? And so it's saying that this map here, so you have two maps here, right? And their difference is really D then the HI, or you could go HI and then D, right? When you add those together, then you get this equivalence. Okay, and so we have this. So this is what a chain homotopy is, right? And then just apply F, right? So you get F, so you get this F of D, F of H plus F of H. Okay, and of course I'm omitting the subscripts here. But I mean, and if we're just going to be abusive about the subscripts, this is just D again. And this is also D. But this is D for the image of the chain complex. Okay? So that shows that those two things are homotopic. Okay? So in particular, right, so all right. So what does that mean? So that means that okay, so now let me give a definition. Okay, so okay, so let's do some notation. Okay, so if A is an R module and P is a projective resolution, of A, and F is an additive functor, all right. So we have this complex, right? So we had this complex where you take F of P. Okay, and then this is some notation that we're going to do. We're just going to call this LF of P. Okay, so this is a definition. Okay, so in particular, so this depends on a choice. So note this thing looks like it depends on a choice of P. Okay, so in particular, right, this LF is a chain complex. and then the left derived functor, ln of f. Oh, sorry. Let's call this, sorry, LF of A. What I wanted to call this. Okay. So LF of A. So this is the left derived. So the nth left derived functor.
Is that the resolution you get from like constantly taking the kernel and working backwards?
So the projective resolution. So that's what would give you a free resolution. Yeah, the one that we constructed. Yeah. So that would give you, and that would be an example. So since free implies projective, then you have that. So a lot of these things are not very constructive right now. And in order to make things constructive, you do work with things like free resolutions. Yeah. Yeah. That's the way to think about it. Yeah, exactly. Yeah. So there's kind of like two problems in homological algebra, right? One of them is like defining things so that things are computable, right? And the other thing is defining things so that things are functorial and you can like transfer results. And right now I'm kind of doing the functorial stuff right now. But yeah, that's true, right? You could take one of those free resolutions to be one of these projective resolutions. Exactly. So this is Hn of LF of A. Okay, and remember this thing here is the cohomology that you get from this complex, right? So it's the cohomology of this chain complex. Okay, and so you'll see this notation a lot. Same thing with, same thing with injective resolutions. And right derived functors. Okay. So, but except for we R f of A is going to be f of I bullet for some choice of injective resolution. Okay, and then the right derived functor is you take your injective resolution, and then you'll take the cohomology of f applied to that functor. Okay, so right, so we have this. These are left derived functors. Okay, and so the lemma that I want to say is that lemma is that LF of A is well defined up to homotopy equivalence, chain homotopy equivalence. Okay, in particular, any two. So if I have two, okay, so let me prove this. So okay, so what's the proof here? Well, let's do this. Let's do this. Let me do this. Let's do two. So given morphism A to B, there's a well-defined map there's a map here, A to LF of B, which is well defined, is unique up to chain homotopy. Homotopy and chain homotopy. Okay, so let me kind of just do this part of the proof. Okay, so let's do the proof here. Okay, so what we'll do is Okay, so given, so let's do the part 2 first. Okay, so so what we do is we take two projective resolutions. So A and Q to be two projective resolutions. Okay, then so by the lifting property. All right. All right. So maybe we should give them names. This is epsilon. This is eta. Okay. So let phi. Let me just be clear what I mean, since I've been talking about these things as morphisms of complexes. Okay, so this is maybe a little bit abusive. So before we were talking about epsilon as a map from P0 to A, but here is what I mean. So here you have P0, A, and maybe we can call this epsilon 0, and then we have P1, P2. All right, and then this complex where you just stick A in degree 0 looks like this. Oh. That's not good. Okay, so this is what I mean by this epsilon map. And then this is a quasi-isomorphism. And those are, of course, projective. Okay, and so let phi be a morphism. Right, and so what I'm trying to show here is I'm trying to show that this is a functor. Okay, so but it's not quite a functor, right? Because of the choice of projective resolution. So it's like a functor up to homotopy. So let phi be a morphism. Okay, and so then by lifting, the lifting lemma, so we have a map, a chain map here, F bullet from P bullet to Q bullet. So lifting the resolutions, A to B. Okay, and so what that means is that the obvious diagram that we want to write down commutes. Okay. So, all right. So what we said, but what we saw before is when what happens is we get a map now of chain complexes. So after applying F, so we get a map of chain complex. Get a map, and so this is, by the way, this thing here is unique up to chain homotopy. And so after applying F, we get a map here. P bullet, F of Q bullet, right? And so this is also unique up to chain homotopy. Okay. All right, so that's great, right? So so this is what we wanted to show, right? That there was a map here from here to here that's unique up to chain homotopy, right? So that proves this part. Okay, so it's that chain homotopies are preserved, and we have this lifting property. So in particular, let me, I guess, so there's something else we can get from this, right? So note that after taking homology, what happens? So then we get a map here. And so again, let me just say this is LF of A. This is LF of B. Okay, so yeah, we get this map. So after taking homology, this gives a unique map. Because homotopy classes of maps HIFP bullet, HIFQ bullet, and this is because so this is because homotopy equivalent, so chain homotopic morphisms of complexes, so chain morphisms of complexes induce the same map on homology. On homology. Okay, in particular, the map from in particular, what this is saying is that, so the point of this is that if you have a map from F from A to B, right, this implies that we have a unique plus resolutions, right? So there's a choice of resolution of A and a choice of resolution for B. Then what does this tell us? That tells us that HI of so that this gives us a map here from the right derived, or sorry, the left derived functor. Okay, so let's suppose that for every object in the category you'd pick a resolution, right? Then that gives you a functor, right? It means it gives a functor if you picked resolutions. Okay. Okay. So what about this part one, right? I said that this thing was well defined up to homotopy equivalence. Okay. So we've actually proved more here, right? So in this process, what else did we prove? So we proved that. Okay. So we proved. Oh well. Okay. So I guess I need to say a little bit more. Okay. So I guess this proves the following. Of projective resolution for each object A of our category. And our category in this case is R modules, but it's not so important. Then the left derived functors are functors. Okay. Okay. So all right. So in particular, what do I mean by that? I mean exactly the statement that we said before, that you have this unique map here, given a map here after you choose a resolution from A to B. Okay. So what about this part one here? Part one was saying that this thing is well defined up to homotopy. Okay. So in the special case, so for part two, in the special case, where A is equal to B, then what happens? So then we get maps. We have two projective resolutions. Of A. So we'll have A here. We have the identity here. This is the identity on A. Then we had one projective resolution here, and then we had another projective resolution here. And then there's this thing that lifts. So this is our choice of phi. And then we have this thing that lifts. Okay. And so note that we have so this thing here. Similarly, okay. So we can also extend this like this. There's also a map here. If we do the identity again, right? And we get some map here like this. And so we have a map of chain complexes, right? And so note that you know, by uniqueness of chain homotopies, sorry, of the morphisms of chain complexes, the lifts up to homotopy. So the map where I do G and then F must be homotopic to the identity on this chain complex. So like there is already a map from the chain complex P to the chain complex P, and because we have that map, right? This in the map is unique. This composition, well, it's a map of chain complexes, so it must be homotopic to the identity by uniqueness, right? Similarly, right? We have that FG must be homotopic to the identity on Q. Okay, so the two resolutions are homotopy equivalent. Okay, and okay, so now we have two resolutions that are homotopy equivalent, and so hence so this means that so then by functorality of homotopy, so okay, so we have two homotopy equivalent resolutions. Okay, and so since being homotopic, so since the relation is homotopic, is preserved under the functor f, and the identity is the identity is preserved under f. So you know the identity has to map to the identity under this morphism, and then in terms of chain complexes, if you have two sorry, maybe, and if you have two homotopy equivalent things, they'll become homotopy equivalent. Or you have two maps that are homotopic, they're still homotopic under F. Then this proves that that this functor, or this complex, in this complex, so these are homotopy equivalent. Okay. All right. So in particular, there's chain maps from one to the other, right? And their composition, if you go to one and then back, then that can be shown to be homotopic to the identity. Okay. And so that proves that this complex here, where is it? That this thing here is well defined up to homotopy equivalence. So what I did is I took two resolutions, I made the complex, and then I showed that the two complexes were homotopy equivalent. Okay, so this proves up to homotopy equivalence, chain homotopy equivalence. Okay, so all right.
Homologies are kind of
yeah, the homologies will be isomorphic. Yeah,
because they're homotopy equivalent. Okay.
Yeah, exactly. So yeah, what does it mean? So it means that. So again, what does this mean? It means that there's maps Yeah, their homologies will be the same. All right, so so we have a map here. Right. So there's maps here. There's a chain map here, and there's a chain map here, and F, G. So you G then F. So this is homotopic to the identity on Q bullet, and then G, F is homotopic to the identity on F bullet, on P bullet. Okay, and so the other claim that I have is that so these functors are well defined up to a unique isomorphism. So I think I already said that. So this gives a resolution. So in particular, so we have this. So since all these maps here, since all these G's, so notice that the F's and the G's are unique up to homotopy equivalence, right? So these things here. Yeah. I guess I already said that. So this is, but also, okay, I said the composition is unique up to homotopy equivalence. This is unique up to homotopy. And this thing is also unique up to homotopy equivalence. Homotopy equivalence. Okay, and so what happens here? So because these maps are unique up to homotopy equivalence, right? This implies, okay, so this the map here. Oh, that's okay. This map here. Sorry, this F Q bullet. So this map is unique up to homotopy equivalence. Oh, I guess I already said this, but okay, anyway. I did this in the first part when I was doing morphisms, but it doesn't hurt to say it again. Right, so this map is unique up to homotopy equivalence, which implies that the map on homology so this is unique up to this is unique up to isomorphism. So this gives an isomorphism. This gives a particular isomorphism here. So since this is unique up to homotopy equivalence, this thing gives an isomorphism here. So all of so in particular these guys here, the functors, Li of Fa are unique, or the I guess these objects here, the objects are unique up to unique isomorphism. Okay, so so what does that mean? It means if I have two chain complexes, right, or two resolutions, right, I do this process and I make the thing, right? I make this left to right functor. Okay, I know that these things will be homotopy equivalent. Not only that, I know the map up to a homotopy equivalence. So after taking homology, that gives you the unique isomorphism between the two homology groups. Okay, and so that's the uniqueness up to unique isomorphism thing. So the unique isomorphism is determined by the unique homotopy class of chain maps. Okay, so yeah.
It's kind of like classes of resolutions, in a sense, then.
Yeah, exactly. They're like yeah. You have resolutions, but you have your resolutions up to an equivalence class. Yeah.
Exactly.
And that's okay. Exactly. So there's a sequence of videos that I have on derived categories, right? And so to do derived categories, you first consider this thing called the homotopy category. In the homotopy category, essentially you take only chain maps up to homotopy equivalence. And so that's why people start to consider derived categories, is to deal with that homotopy equivalence issue.
Lump all those together, yeah.
Okay. Yeah. So the motto is that when you do these sort of modifications of categories, is that the objects are going to stay the same, right? But you change the morphisms, and the morphisms, just like in topology, right? So like to make in topology, to make the homotopy category, right? So you just take morphisms, but you mod out by homotopy equivalence of morphisms, right? Yeah. Yeah, and so we can do that. So yeah, so I think this kind of covers the well-definedness issues. So the well-definedness issues that I wanted to do. So I'm going to stop this here, and then I'm gonna continue with the other part of this. So I can just kind of like make a cut here.